It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good night, everybody. Welcome to Tibbetts Physics. What is crappin'? Today we're going to talk about waves and the properties of waves. So let's first define a wave in terms of physics. So all a wave is the motion of a vibratory disturbance that transfers momentum and energy but not mass. So today we're just going to talk about properties of waves. In the next video we'll talk about types of waves. Let's look at a sine wave first and label various parts along the sine wave to help us understand the aspects of a wave. So we'll start with the origin. We'll label that point A, the top part point B, C, D, E. Let's go halfway up. We'll call that F. To the top G, halfway down H, and back at the origin F. So I'm sure you've learned parts of waves before, but we're going to go through all the aspects together today. The first thing we can look at is the amplitude of a wave. The amplitude of the wave is the distance from the origin to the crest, or the highest point. It can also be from the origin to the trough, or the lowest point. So since it could be the highest or the lowest, instead of using distance, we'll say the displacement. So it's the displacement from the highest, from the origin to the highest or lowest point. And just a reminder, the highest point is called the crest, that'd be point B and G, and the lowest point is called the trough, that'd be at point D. So that's the amplitude. The other distance that we can measure is called the wavelength. And in physics, we represent wavelength with the Greek letter lambda, pronounced lambda. And we can easily define it as the distance from crest to crest, or the length from crest to crest. So in this case, from B to G. So the distance from crest to crest. In this case, it could be from B to G. But that's a very specific case. It could be other points that are the same length. So it could also go from A to E or C to F. So if we want to be more generic, we could say it's a distance from from 2 points when the wave repeats itself. So point B and then point G, we could see the waves at the same aspect. And then A to E or C to F. So we could also say, or the distance from when the wave repeats itself. So we'll add from A to E and C to F. Notice these points are 360 degrees away from each other, or if we want to be in radians, we could say 2 pi radians. So we could also add for wavelength, or, again, we'll get rid of that period, or 360 degrees, which is 2 pi radians, away from each other. At the beginning of the year, we talked about pendulums and the period of the pendulum, and that was the time for a pendulum to swing back and forth once. And we could apply this to a wave. Period is capital T, and all it is the time to complete just one wavelength. So the time to complete one wavelength, or one lambda. Since it's a time, the units for period are seconds. The reciprocal of period, the time to complete one wavelength, or the time per one wavelength, would be the opposite. It'd be the number of wavelengths or cycles per time, and it's called the frequency. And we'll label that as lowercase f. So the frequency is the number of cycles or wavelengths, where one cycle is one wavelength, for every 1 second. So it's the number of cycles per second. The frequency, again, is the reciprocal of the period. So the frequency is 1 over the period. And we can also say that the period is 1 over the frequency. The units for frequency, since it's 1 over the period, would be 1 over seconds, and that's equal to a hertz, which is abbreviated as capital H, lowercase c. So hertz for frequency. Since we have units of time, which would be the period, and since we have the wavelength, which would represent the distance, I forgot to mention the units of wavelength are meters, we can then calculate the speed of the wave. So if we're going to assume that this wave is moving at a constant velocity, so its speed is distance over time. And if we look at just one wavelength, the distance that wavelength would travel would be lambda, so the speed is lambda over the time. But since we're looking at one wavelength, the time to complete one wavelength is the period, so we could do lambda and turn time over period. But lastly, we know that the frequency is 1 over the period, so we could turn 1 over the period into frequency, and that leaves us with speed is equal to the wavelength times the frequency. So V equals lambda f. Now if we're looking at a wave that's moving at a constant speed, if we change the frequency by increasing it, so there's more cycles per second, that means that the wavelength is going to shrink in order for us to have a move at a constant velocity. So they're going to get closer together. The wave crests will get closer together as we increase the frequency. If we do the opposite, decrease the frequency, that means less cycles per second, the wavelengths are going to increase. So frequency and wavelength have an inverse relationship. What we're going to do next is look at points along the wave. So we have our letters labeled. We're going to look at the relationship between those points. The first one is called in phase. When points are in phase, that means they are points that are increments of one wavelength away from each other. So instead of saying increments, we'll say n lambdas. That means they can be one wavelength away from each other, 2 wavelengths, 3 wavelengths, and so on. But it has to be a whole number. N lambdas away from each other. So if we look at our sine wave, we know our wavelength is BG, so those are one wavelength away from each other. In this case, all of our options are only one wavelength, so they're all of our points that we define as our wavelength. So BG, AE, or CF. And the other end of the spectrum is points that are out of phase with each other. So out of phase. So that means they're anything but one wavelength away from each other. So we can say points that are, we could use any points, but we're going to use 90 degrees, 180 degrees, or 270 degrees away from each other. So we have to take out our trig book and remember what points that are 90 degrees, 180, and so on away from each other. So let's look at 90. If we start at point A, from the origin to the crest, that's 90 degrees. B to C is 90, C to D is 90. So we'll say A to B, B to C, C to D, and so on. The next would be 180 degrees, so that's half a wavelength. If we start at A to B is 90, B to C is 90, so that means A to C is 90. So we could say A to C. We can also go C to E and E to F. But we could look at D. D to E is 90. E to G is 90. So we can also say D to G is 180 degrees. And then the last set of out of phase points we'll look at is 270 degrees. It's 90, 90, 90. A to B, B to C, C to D. So A all the way to D is 270 degrees. A to D. And if we look at, let's say, C to D is 90, D to E is 90, E to G is 90. So C all the way to G is 270 degrees. And so on. Okay, 2 more things. We're first going to look at what would it look like if you are sitting in the ocean and a wave comes by you. And then we're going to calculate the wavelength of a radio wave. So let's say you're sitting at point E. We'll label this P. And the wave, we're going to say, is moving towards the right. And the question is, what direction would you move in the next instant of time? So to do that, let's look at an actual wave moving. Let's see here. Okay, so here we have a wave. It's moving to the right. Let's imagine that you're this point right here, this green point along the orange line. So when I press play, watch what happens to the green point in the next instant of time. Notice that that point only moves up and down. That's because this wave is not transferring mass, which would be u at that green point. It's only transferring energy. So if we go back to the beginning, in the next instant of time, let's look at what's happening behind you. So a giant water wave or ocean wave is coming towards you. That's going to cause you to move up. And then once you're at the crest, you're going to start moving down. And what's behind you is the trough, so you're going to continue moving down. So to determine the direction you're going to move along a wave, in this type of wave, it's going to either be up or down. And all you have to do is look at what's happening behind you, or what's approaching you. So in this case, at point P, what's approaching you is the trough of the wave, so you're going to start moving downwards. If we go to point C, the crest of the wave is approaching you. That means you're going to move upwards. Okay, lastly, let's just calculate the wavelength of a radio wave that you're listening to in your car. So let's say that you're listening to 104.1 Binghamton Hits music station. When you tune to 104.1 on your FM radio, that's the frequency of the wave. So the frequency is 104.1, but it's not just 104.1, we have to multiply it by 10 to the 6. So 104.1 times 10 to the 6 hertz is the radio station you're listening to. The speed of a radio wave, we'll learn this later, is the speed of light, which is 3.00 times 10 to the 8th meters per second. And you might ask yourself, how long is that wavelength of 104.1 times 10 to the 6 hertz, or that radio station? That's what we're going to calculate. So lambda equals question mark. So all we have to do is use our speed formula for a wave. Speed equals lambda f, which means lambda is v over f. And all we have to do is plug and chug. So 3.00 times 10 to the 8th meters per second over the frequency 104.1 times 10 to the 6th hertz. And we do that and we get a wavelength of 2.88 meters. So that's the one wavelength of the radio station that you're listening to, 104.1 KISS FM. Hope you enjoyed this video and found it useful. If you did, please like and subscribe, and I'll see you next time.